We live in a universe governed by the relentless laws of entropy. In our world, things fall apart. Steel rusts, returning to the iron oxide from which it was smelted. Plastic degrades, breaking down into microscopic polymers that choke our oceans. Wood rots, consumed by the biological cycle of decay. The structures we build are temporary. They're fighting a losing war against time. But there is one exception. There's one material that stands apart from this cycle of degradation. A material that occupies a strange, liminal space between the elemental and the eternal. Glass. To the physicist and the chemist, glass is a paradox. It defies easy categorization. It is rigid to the touch, hard enough to cut flesh, yet atomically it is not solid. It is an amorphous, solid, a state of suspended animation. When silica sand is melted and cooled rapidly, its atoms do not have time to organize themselves as a rigid, orderly lattice structure of crystal. Instead, they are frozen in a chaotic, liquid-like arrangement. They are trapped in a moment of incident. This atomic chaos is not a flaw. It is the material's greatest strength. Because it has no crystalline structure to disrupt, glass has no memory of the past. It can be melted down, reshaped, and cooled again, not just once, but infinite times. It does not lose its strength. It does not lose its clarity. It does not lose its purity. A bottle made today can be melted down and reborn in the year 3000, and chemically, it will be indistinguishable from the day it was first forged. However, this potential for immortality is theoretical until it is enacted by human beings. We are standing at the gates of a modern glass beneficiation program. This facility is the bridge between the end of a product's life and the progress. It is a machine of colossal scale, designed to ingest the chaos of human consumption and transmute it back into pure raw potential. The raw material for this facility does not come from a pristine mine deep within the crust of the earth. It comes from the urban mine, the sprawling, chaotic, and messy network of our cities, suburbs, and industrial areas. Every day, a fleet of heavy trucks arrives here, their engines groaning under the weight of the city's workers. They carry waste, known in the industry as single-stream recyclables. Ideally, this would be a pure stream of glass vessels. In reality, it is a nightmare of contamination. When a truck tips its load on the concrete tipping floor, we do not see a river of onions. We see a disgusting gray slough. It is a mixture of broken shards, crushed aluminum cans, plastic bags, rotting organic food waste, medical debris, cardboard, and ceramics. To the uninitiated observer, this pile looks like garbage, destined for a landfill. To the plant manager, it is a complex puzzle that must be solved at a rate of 50 tons per hour. The sensory experience of the tipping floor is overwhelming. The smell is a pungent cocktail of stale beer, fermenting sugar, and diesel exhaust. The sound is deafening, a constant, rhythmic crashing of silica against steel, a roar that vibrates in the chest. Dust motes dance in the shafts of sunlight, piercing the high warehouse windows. But this is not ordinary dust. It is a mixture of paper fibers and microscopic glass particles. The first challenge in this process is simple physics, liberation. The glass arrives trapped. It is inside plastic bags tied in knots. It is stuck inside wet cardboard boxes. It is glued to paper labels. We cannot sort what we cannot see. The material is pushed by heavy loaders into the intake hopper, a steel throat that swallows the waste and feeds it onto a massive, inclining rubber belt. The material travels up to the bag breaker. This is a rotating drum equipped with metal teeth. It is designed to rip open plastic trash bags without pulverizing the glass inside. This is a delicate balance. We want the glass to break. Broken glass, or cullet, is easier to process, but we do not want to crush it into dust. Glass sand is difficult to color sort and often lost to the filtration systems. We need shards. We need pieces large enough to be recognized by a machine, but small enough to flow like a liquid. As the stream moves forward, it enters the realm of mechanical separation. This is the dirty side of the plant. The objective here is not perfection, it is volume reduction. We must remove the bulk of a non-glass material. The stream passes over a series of disc screens and troughs. These are rotating shafts with interlocked rubber discs. The concept relies on gravity and geometry. The heavy, three-dimensional glass shards fall through the gaps between the discs, dropping onto a lower conveyor. The lighter, two-dimensional materials, the flattened plastic, water bottles, the newspapers, the cardboard pizza boxes float over the top of the rotating discs and are carried away to a separate recycling stream. It is a violent process. The facility shakes with the energy of separation. But even after this initial screening, the glass is far from clear. It is mixed with ferrous metals, steel bottle caps, jar lids, wires. To address this, we employ massive, suspended electromagnets. These are positioned directly over the conveyor belts. As the stream passes underneath, the magnetic field reaches down and invisible. You can see the rusted steel caps defying gravity, leaping from the belt and snapping onto the magnet's face, before being scraped off with a scraper. But the most insidious enemies are the steel caps or the cardboard boxes. The true enemies of the glassmaker are the materials that look like glass, act like glass, and feel like glass, or are chemically incompatible with glass. We speak of the CSP contaminants: ceramics, stones, and porcelain, a fragment of coffee mug, a piece of Pyrex heat-resistant cookware, a stone picked up from a driveway, a piece of brick from a demolition site. These materials are the assassins of the recycling process. They have a much higher melting point than standard soda lime glass. If a single piece of ceramic, no larger than a grain of rice, makes it through this plant and enters the furnace, it will not melt. It will remain a solid inclusion in the finished bottle. In the industry, this is called a stone. When a new bottle is formed around this stone, the cooling rates differ. The glass contracts, but the ceramic stone does not. This creates a halo of immense internal tension, a stress point waiting to release. When that bottle is later filled with carbonated soda or pressurized beer, the stress becomes too much. The bottle explodes. Not cracks, explodes. Therefore, the tolerance for ceramic contamination. This facility is practically zero. It is a hunt for a needle in a haystack where the needle looks exactly like it. To begin this refinement, the stream passes through the air knives and cyclone aspirates. These are systems that use high-velocity aerodynamics. The conveyor belt ends, and the material falls through a curtain of brush air. The heavy glass falls straight down, obeying Newton's laws. But the lighter contaminants, the shredded paper labels, the aluminum foils, the plastic caps, are caught by the updraft. They are sucked away into huge ductwork systems, swirling like a tornado before being deposited in a compactor. The air is scrubbed, filtered, and returned to the plant, while the glass continues its journey. We are now left with extreme ends, roughly 80% glass, but it is still a dirty, mixed-color aggregate. It contains aluminum rings, lead crystal, and those deadly ceramic stones. The mechanical age has done all of it. We must now cross the threshold into the digital age. The material is about to leave the roar of the crushing floor and enter the silent, strobing world of the optical swirl. This is where the true alchemy begins. We leave the dusty, chaotic mechanical pre-processing area and pass through heavy vinyl curtains into the optical sorting hall. The atmosphere here changes. Instantly, the air is cooler, scrubbed of dust. The noise shifts from a low-frequency rumble to a high-pitched pneumatic hiss. This is the brain of the operation. We are no longer relying on the crude physical properties of weight and size. We are relying on the speed of light and the precision of computation. The glass stream, now crushed into uniform pieces called cullet, is spread out on high-speed accelerator belts. It is moving at nearly 3 meters per second, a blurring river of sharp edges. The human eye cannot track individual particles at this speed. It sees only a gray stream, But the machines lining this hall do not see a blur. They see every single particle as a distinct, individual object. These are optical sorters, the most advanced machines in the recycling ecosystem. As the glass flies off the end of the accelerator, it enters a momentary state of free fall. For a fraction of a second, the glass is suspended in the air, separated from its neighbors. In that micro moment, it is bombarded with light. High-intensity LED strobes and laser arrays illuminate the glass from the front and back. Sensors capture the light that passes through the shard, transmission, and the light that bounces off it, reflection. This data is fed into a central processing unit that operates at speeds rivaling a supercomputer. The computer asks 3 questions of every single shard, millions of times per hour. First, is it opaque? If the light cannot pass through, it is not glass. It is a stone, a piece of ceramic, or a piece of porcelain. It must be destroyed. Second, what color is it? The sensors analyze the spectral signature. Is it the deep brown of amber, which protects beer from ultraviolet light? Is it the vibrant emerald
Here's
green
the manifest
of a wine
and the
bottle?
permit.
Or is it the crystal
All
clear
right, everything
flint
looks
glass
to be in
used
order.
for
You're
food
good
jars
to
and
go.
spirits? Third, what is its chemical composition? Using X-ray fluorescence and infrared sensors, the machine checks for heat-resistant glass like borosilicate or leaded crystal. These have different melting points and are considered contaminants. The decision is made in milliseconds. If a shard is identified as contaminant, say a piece of white porcelain, the computer calculates its exact trajectory. It predicts exactly where that shard will be in 5 milliseconds. It then sends a signal to an array of high-speed pneumatic ejectors positioned below the flight path. Listen, a single, precise blast of compressed air fires from the nozzle. It hits that specific piece of porcelain in midair, knocking it out of the main stream and into a reject chute. The good glass, untouched by the air, falls into the accept chute. This happens hundreds of times per hour. Second, it is a ballistic ballet, a war fought with invisible bullets of air against an army of debris. The result of this optical gauntlet is purity. The stream is separated into 3 distinct piles. We have the amber cullet, a rich, dark mound that looks like a pile of garnets. We have the green cullet, shimmering like crushed emerald. And we have the flint cullet, a pile of diamonds, clear and sparkling. This material is no longer waste. It has been elevated. It is now a commodity, ready to be sold back to the glass manufacturing plant. This cullet is loaded into trucks and driven to the batch house of the glass factory. Here, it ceases to be a finished product and becomes an ingredient. Glass making is, at its heart, a branch of high-temperature chemistry. You cannot simply melt old bottles to make new ones. You must balance the chemical equation. The cullet is fed into massive silos, standing alongside silos of large materials. To make the perfect glass batch, we mix the recycled cullet with 3 primary ingredients. First, silica sand, silicon dioxide, the glass former, the backbone of the molecular structure. Second, soda ash, sodium carbonate, which acts as a flux. Pure sand melts at over 2,000 degrees Celsius, a temperature that is economically ruinous to manufacture. Soda ash disrupts the silicon bonds, lowering the melting point to a manageable level. Third, limestone, calcium carbonate. If you made glass with just sand and soda, it would be water soluble. Your glass of water would dissolve into the water it held. Limestone acts as a stabilizer, making the glass durable and insoluble. But cullet is the star of this recipe. For every 10% of cullet we add to the mixture, we reduce the furnace's energy consumption by nearly 3%. Why? Because cullet has already been melted. The chemical reaction has already happened. It does not need to be forged. It only needs to be reheated. It melts at a lower temperature than the raw sand. It is like adding hot water to a boiling pot. It accelerates the process. Modern factories driven by sustainability, goals and energy costs push the limits of this chemistry, often running recipes that are 60, 80, or even 90% recycled cullet. The mixture of sand, soda, lime, and cullet is, weighed with pharmaceutical precision. If the ratio is off by even a fraction of a percent, the glass will be too brittle or too soft or the wrong color. The batch is mixed in giant rotating drums until it is perfectly homogeneous. It is kept slightly damp to prevent the fine powders from separating or dusting into the air. This damp, sandy mixture is then carried on enclosed conveyors to the doghouse. This is the intake port of the furnace. We are standing on the precipice of the inferno. The doghouse feeds the batch into the melter using a reciprocating charger that pushes blankets of raw material onto the surface of a lake of molten lava. We are now looking into the heart of the beast, the regenerative gas furnace. This is not a simple oven. It is a structure the size of a house, built from specialized refractory bricks capable of withstanding temperatures that would melt steel like butter. Inside, the temperature is maintained at a terrifying 1,500 degrees Celsius. The furnace runs 24 hours a day, 365 days a year. It will run for 15 or 20 years without ever stopping. It cannot stop if the heat is turned off. The molten glass will freeze into a solid block of rock weighing hundreds of tons. The refractory bricks, cooling down, will contract and crumble. To turn off a glass furnace is to destroy it. It is a continuous, living beast that must be fed constantly. Inside the furnace, a violent transformation occurs. As the batch hits the molten bath, the solids dissolve. The carbonates decompose, releasing massive amounts of carbon dioxide gas. The mixture bubbles and boils violently. This creates a problem. You cannot have bubbles in a glass bottle. A bubble is a weak point. It ruins the aesthetic and strength. So the glass flows from the melting zone into the fining zone. Here, the temperature is raised even higher. We add chemical fining agents like sulfates, which release large gas bubbles. These large bubbles rise rapidly through the molten gas, sweeping up the tiny micro bubbles that way, like a net catching fish. They drag the trapped gas to the surface, leaving the glass underneath perfectly clear. The molten glass, now fine and free of seeds and blisters, begins to flow toward the forming head. It passes through a submerged throat, a ceramic barrier that schemes off any floating impurities on the surface, ensuring that only the pristine glass from the bottom of the tank moves forward. It is a liquid, honey-like river of liquid, ready to be given shape. The molten glass, purified and fine, flows from the main furnace tank into the forehearts. These are long, narrow refractory channels that act as the temperature control system for the forming process. In the furnace, the glass was 1,500 degrees Celsius, too hot and too fluid to hold a shape. If we try to mold it now, it would run like water. In the forehearts, we gently cool the glass down to a working temperature of approximately 1,100 degrees Celsius. At this temperature, the viscosity of glass changes dramatically. It transforms from a watery liquid into a thick, viscous syrup, glowing a vibrant, incandescent orange. It is now ready to be sheared. The glass reaches the end of the foreheart. Here, a ceramic plunger pushes it. Molten stream through a hole in the floor called the orifice. As the glass extrudes, massive mechanical shears, scissors made of specialized high-temperature alloy, snip the stream. These shears cut the glass into precise, glowing logs called gobs. The precision here is absolute. Each gob must be the exact weight required for final bottle. If the bottle is designed to weight 200 grams, the gob must be 200 grams. If it is 199 grams, the bottle walls will be too thin and it will burst. If it is 201 grams, the machine will jam or the internal volume will be low. The gobs fall through a series of delivery chutes, lubricated by oil and graphite, sliding down into the machine that will define their existence. We are looking at the IS machine, the individual section machine. This is the rhythmic, clanking, hissing heart of the glass factory. It is a mechanical octopus, a row of 10 or 12 identical sections working in perfect harmony. The noise is incredible. a symphony of compressed air, slamming metal, and sizzling oil. The process used here is a race against thermal shock. Glass wants to freeze. As soon as it touches the metal, molds, it begins to harden. We have seconds to shape it. The gob falls first into the blank mold. A plunger moves up, or compressed air blows down, forcing the glass into the bottom of the mold. Form the neck and the finish, the threads where the cap will go. This is the only part of the bottle that is finished at this stage. The glass is then blown upwards to create a hollow space, forming a parison. A parison looks like a shrunken, thick-walled version of the final bottle, glowing red-hot. A mechanical arm that swings the parison 180 degrees over into the blow. Mold. This is the final shape. The parison hangs there for a split second, stretching under its own weight. Then, the mold closes around it. A blowhead descends and blasts compressed air into the interior. The glass inflates like a balloon. It is forced against the cool iron walls. The contact with the metal sucks the heat out of the glass instantly, freezing it into its final shape. All of this, the cutting, the loading, the flipping, the blowing, the opening, happens in less than 10 seconds. A standard IS machine can produce 500 bottles every minute. It is a blur of fire and motion, orchestrated by electronic timing drums and servo motors. The bottle is now formed, sitting on a conveyor belt, glowing at dull red, but it is in critical danger. The rapid cooling has locked immense tension into the glass skin. The outside is cool, but the core is still hot. The differential contraction creates stress. If you were to touch the bottle now, it might shatter spontaneously. It is a ticking time bomb of potential energy. It must be healed. The bottles travel in a long, marching phalanx into the annealing layer. The layer is a massive tunnel oven, often 30 meters long. Inside, the bottles are reheated to about 600 degrees Celsius, a point where the glass becomes slightly soft again, allowing the internal stresses to relax. Then, they're cooled down very slowly over the course of 45 minutes. This controlled cooling aligns the atomic structure, removing the tension and making the glass durable. Emerging from a layer, the bottles enter the cold end. Here, they're treated with a cold end coating, usually a microscopic layer of polyethylene wax. This makes the glass slippery. It allows the bottles to bump and slide against each other on the high-speed filling lines without scratching. Friction is the enemy of glass strength. A scratched bottle is a weak bottle. Finally, we reach the inspection line. In the old days, humans sat and watched the bottles pass. Today, it is total automation. The bottles enter the squeeze tester. This machine grabs every bottle, applies hundreds of pounds of compressive force to the sidewalls. If the bottle has a hidden crack or a thin spot, it shatters here inside the safety cage rather than in the consumer's hand. They pass through sidewall inspection machines. Cameras spin the bottle 360 degrees, taking dozens of photos. Software algorithms look for birds' wings, thin strands of glass inside, blisters, bubbles, and stones. They pass through plug gaugers that mechanically check the internal diameter of the lid to ensure the cork will fit perfectly. The reject rate is tracked in real time. If the machine detects a defect rate of even 0.1%, alarms sound. Perfection is the minimum standard. The finished bottles are swept onto pallets by robotic arms, thousands a day. Time, creating towering walls of glass. They're wrapped in plastic, ready to be shipped to the brewery, the vineyard, or the food processing plant. But look closely at one of those bottles before it leaves. It is more than just a container. It contains history in its atoms. There might be silica sand melted by a Roman artisan 2,000 years ago. There might be a shard of soda bottle from the 1950s. There might be the remains of a pickle jar that was put away last week. Glass is the ultimate traveler. It changes shape, but it never changes substance. It moves from the liquid fire of the furnace to the cool shelf of the supermarket, to the chaos of the trash bin, and back to the fire. In a world drowning in disposable plastic waste that will linger for centuries as pollution, glass offers a different path. It offers the infinite loop. It is clean. It is chemically inert. It is beautiful. And as long as we have the will to collect it and the technology to refine, it is immortal. This is the alchemy of industry. This is the eternal promise of glass. To understand the true urgency of the machinery we have just witnessed, one must look away from the factory floor and toward the riverbeds and coastlines of the world. We tend to think of sand as an infinite resource. It covers our deserts, it lines our oceans. But this is an illusion. Desert sand, shaped by wind, is too round and smooth to lock together. It is useless for construction or manufacturing. The jagged, angular sand required for concrete and glass comes from water, from rivers, lakes and shorelines, and we are running out of it. Humanity consumes 50 billion tons of sand every year, making it the second most consumed natural resource on the planet. We are dredging riverbeds, collapsing banks, and destroying ecosystems to feed the insatiable maw of global urbanization. In this context, the glass recycling plant is not merely a waste management facility. It is a strategic conservation asset. Every ton of cullet used in that furnace preserves 1.2 tons of raw natural resources. It keeps the dredgers out of the rivers. It leaves the coastline intact. The bottle you throw in the bin is a direct defense against the erosion of the natural world. However, the glass industry faces a formidable adversary, one that physics dictates cannot be ignored: gravity. Glass is heavy. In an era of globalized supply chains, weight is carbon. Shipping a truckload of empty glass bottles 500 miles consumes significantly more diesel than shipping a truckload of plastic pouches. This is the glass paradox. It is the most sustainable material in terms of toxicity and infinite reusability. But it can be the least sustainable in terms of transport emissions if the logistics are not tightly controlled. This reality has forced a revolution in engineering known as lightweight. We return to the IS machine and the design of the bottle itself. 30 years ago, a standard wine bottle weighed 500 grams or more. Today, through advanced computer modeling and a process called narrow neck press and blow, and MP, that same bottle weighs 300 grams, yet retains the same burst strength. How? By redistributing the glass distribution with micron-level precision. In the old blow-and-blow method, the glass wall thickness varied. To ensure the thinnest point was strong enough, the rest of the bottle had to be excessively thin. It was over-engineered. An NPEB uses a metal plunger to press the RIC, ensuring the internal cavity is perfectly concentric. This allows the walls to be uniformly thin, stripping away unnecessary layers. We are removing it. We've got to leave only the muscle. This reduction of 200 grams per bottle, multiplied by billions of units, saves millions of tons of CO2. It changes the calculus of the supply chain, making the infinite loop not just theoretically possible, but economically viable. But the battle for sustainability is not just about weight. It is about the embodied energy. We must talk about the furnace again. That roaring beast at 1,500 degrees is a massive consumer of natural gas. For every kilogram of glass produced, a significant amount of methane is burned, releasing carbon into the atmosphere. This is the industry's Scope 1 emission problem. The recycling plant reduces this. Remember, cullet melts at a lower temperature, but it does not eliminate it. To solve this, the industry is currently engineering the furnace of the future. We are witnessing the birth of oxy-fuel technology. Traditional furnaces burn gas with air, but air is 78% nitrogen. Heating up all that nitrogen just to vent it out the chimney is a thermal waste, and it creates nitrogen oxides, NOx. Oxy-fuel furnaces strip the nitrogen out of the intake, burning pure oxygen or gas. This increases thermal efficiency, reduces fuel consumption by 15%, and cuts NOx emissions by 80%. It is a hotter, cleaner burn. Yet even oxy-fuel is a stopgap. The ultimate horizon is the zero-carbon furnace. Engineers are currently piloting hybrid furnaces that run on 80% electricity, sourced from renewable wind and solar, using molybdenum. Electrodes submerged directly into the glass bath to heat it through resistance, the Joule effect. The remaining 20% of energy required to melt the raw batch blanket on top will come not from natural gas, but from green hydrogen. When hydrogen burns, it produces only water vapor. A furnace running on green electrons and green hydrogen would produce a glass bottle of A. Carbon footprint near zero. This is not science fiction. The pilot plants are being built in Europe today. It is the industrial equivalent of heart surgery, replacing the cardiovascular system of A. Factory while is still running. As we conclude our journey through the cathedral of cycle, we must widen our aperture. We have focused on the bottle, the vessel of our daily consumption. But glass is far more than packaging. It is the defining material of the information age. The silicon age is usually associated with computer chips, but it is equally the age of silica glass. Consider the fiber optic cables that crisscross the ocean floor, carrying the data of the internet. These are strands of glass, drawn so pure that if the ocean were made of this glass, you could see the bottom of the Mariana Trench.
All right,
clearly.
bring it up slowly.
Consider the
Watch
Gorilla
the
Glass
edges.
on the smartphone in your pocket. An aluminosilicate glass
setting it in
strengthened by
now.
potassium salt bath ion exchange. Process, making it tougher than steel. Consider the ultra-thin, flexible glass being developed for foldable screens. Glass that can bend like paper without breaking. The recycling facility we toured handles the low-tech soda lime glass, but the principles of circularity are beginning to touch these high-tech sectors as well. We are seeing the rise of photovoltaic glass recycling. As the first generation of solar panels reaches the end of their 25-year lifespan, we face a tidal wave of electronic glass waste. The technologies we saw today, the crushing, the optical sorting, the chemical refining, will be adapted to recover the high-value silver and silicon from these panels, turning old renewable energy infrastructure into the raw materials of the new. There's also a philosophical dimension to this material. Glass is our window into the universe. It was a glass lens that allowed Galileo to see the moons of Jupiter and dismantle the geocentric model of the universe. It was a glass mirror in the Hubble telescope that revealed the age of the cosmos. And it is glass lenses and microscopes that allowed Pasteur to see bacteria and revolutionize medicine. Civilization, in many ways, is the story of humanity looking through silica to see the truth. The bottle, then, is the humble cousin of the telescope, but it is no less important in a world choking on microplastics, polymers that are found now in the blood of penguins in Antarctica and in the placentas of unborn infants. Glass remains the stoic alternative. It is chemically inert. It does not leach hormone-disrupting chemicals into your water. It does not shed microparticles into your wine. If a glass bottle escapes the recycling loop and ends up in the ocean, it does not poison the food chain. It simply tumbles in the waves, slowly returning to the sand from which it came. It is a benign material. This brings us back to the infinite loop. The facility we entered is not just processing trash. It is maintaining a legacy. It is keeping the material in circulation so that we do not have to scour the earth to find more. It is a testament to the idea that we can build an industrial society that works with the cycles of matter rather than against them. As the sun sets over the Cullet piles outside the planet and mountains of amber, and green glitter like dragon's holes, they are waiting for their turn in the fire. Tonight, they will be melted. Tomorrow, they will be formed. Next week, they will be on a dinner table. And next month, I will be back here. It is a grueling, loud, hot, and heavy process. It requires massive energy and logistical brilliance. But it is worth it, because in this cycle, nothing is truly lost. In the hiss of the air jets and the roar of the furnace, we hear the heartbeat of a sustainable future. A future that is clear, durable, and infinitely renewable. This is the story of glass. The sand that became a star, and the star that became a bottle, forever turning in the hands of humanity.